Okay, so welcome everyone to our webinar. Today we are very, very happy to have Intel coming to present the HPC roadmap and Intel oneAPI. So our speaker today will be Giacomo and Andrea. Thank you very much for coming and thank you very much to share all this information. And please go ahead.
Yeah, so maybe I will do just a very quick intro, 1 minute. So thanks everyone for joining. We are very happy to be here. So I'm one of the account manager for HPC for Intel in Europe. And what I wanted to say, so this session will be divided into really two parts. One part will be on the roadmap and on the hardware side, but I think we'll go quite fast because we really want to focus this webinar on our software discussion, software tools, and also all the programming models and so on, so that we can give you really the view on how to use our tools and what it can do. So again, first phase will be quite fast, and then we'll focus more on software. We are quite a few from Intel attending the session, so I mean, don't be shy. I mean, ask your question as we go through the presentation. You can do that, you know, verbally or also do it on the chat. Again, we are quite a few, so we can either answer directly or also, you know, stop the flow and answer to everyone. So it's all I wanted to say. So our two speakers are from Italy. Andrea first for the hardware, and then Giacomo for the software. So Andrea, please go ahead. Floor is yours.
Thanks a lot, Alex, and welcome everybody to the webinar. So let me start to give you a brief introduction to what will be the roadmap for today. Before starting and giving you details about it, let me give you again a brief introduction to the strategy, to what we are trying to do. So Intel's strategy to get leadership in HPC is basically focusing in three main areas, if you could say: performance, open, and scale, as you can see here. Performance means introducing for us new architectures, a new product, and breakthrough innovation, combining manufacturing, packaging capabilities, and new IP, which are also part of the scale, let's say, area. As you know, we have published and we also have announced a new strategy for that. So focusing on the factory and the manufacturing things and the packaging. As being open, which is the main focus for today's meetings, software is absolutely the key. So it's the glue between the different compute units, like, you know, CPUs, GPUs, FPGAs, etc., etc. And you want to keep it open. For us, is absolutely kind of crucial and a must. And that's why oneAPI, which will be the second part and the relevant part of the today webinar, has become also an open industry standard initiative. And my colleague, as I said, Giacomo, will talk in details about it. Before that, let me give you some details on the hardware side, as we said. So what we have today is the Xeon, the third generation of the Xeon scalable processor. The code name is Iceland, as you may already know. And he already brought some innovation. Some of them, just to mention, it was the introduction of the PCI Gen 4, and also the technologies for security and for what we call kind of security computing, confidential computing, that allow to start also to do some work in scaling, like federated learning for AI, for example. Starting from here, which is obviously the product is available today, we will release new product during this year. The next generation of CPU, which is called in code name Sapphire Rapids. That's, as said, is going to be available in 2022. After that, as part of the innovation, we want to bring new product segment out, and the next one, again, available starting in 2022, will be the first high performance computing GPU, which is called Ponte Vecchio, as you can see here. But that is not the last things that we want to do and we aim to do, which is also to introduce a new product that is aiming to address obviously specific kind of workload, but it's the next generation CPUs together with the HBM memory. And I will talk about that in details in few minutes. After that, a lot of new product will come in 23 and beyond, bringing innovation in all these three kind of area. Let me give you some more details on the CPU side to let you understand what we will focus on and what will be the main innovation. So as I said, on CPU side, we will have Sapphire Rapid in 2022, Annual Rapid will be released in 2023, and then also other generation of CPUs, right, like Granite Rapids. But what we are also doing is we want to, let's say, bring a couple of segments or leverage on a couple of segments, a couple of CPUs, core, which is the P core and the E core. We have seen incredibly high demand for very high efficiency. So it's not just the pure performance, but it's also the power efficiency that in these days drive the selection of the technology. So we will have two lines. So basically one aiming the best performance per core, which is driven by the P core, and one super optimized one, which is the E core that will also allow to drive high throughput computing. And that is what is, let's say, the split for the next generation of CPUs that you will see in the next few years. But let's go back and try to, let's say, focus on what is the shortest, let's say, plan. So what will happen in basically in 2022? What is the focus, right? So let's start talking about Sapphire Rapids and Ponte Vecchio. About Sapphire Rapids, so it's going to bring significant innovation from different standpoints, as I said. So we are using new technology to build the product. So it's not, it's going to be a multi-tile, as you can see here, technology. So leveraging on what we use, the EMIB, to connect all of them together, but will be seen as a single, obviously, CPUs, right? Single die. You will have the next generation of bus or communication. So again, doubling the bandwidth. So PCI Gen 5 is going to be brought into the market, and also new bus for connecting CPUs together, and also the CXL. Another very important innovation, which will be part of the introduction of Sapphire Rapid, is the memory, the new kind of technology. So DDR5 will be introduced. And also, as I was mentioning before, the HBM, and they will talk about it in a moment. The other very interesting things that we are going to bring together with Sapphire Rapid is innovation in what how we do, let's say, the kind of the computing and the capabilities of GPUs. In that sense, we are bringing accelerator integrated in the CPU, so into the package, and we also introduce one of the most advanced innovation, which is the advanced matrix extension, which is the support basically, let's say, for advanced learning instructions, because we want to aim also not just the inference that we were already able to do on our CPUs, but we also aim to do the training part, some of the training workload on that. And for that, we have introduced these new extensions. Moving to the HBM part. So that is going to be the same CPUs, so same Sapphire Rapid, as I said, but it will have HBM2E integrated in the package. So on the socket, you will have up to 64 GB of HBM2E available, bringing significant advantages in the overall bandwidth available, specifically addressing at that point exactly this kind of workload that really needs a lot of bandwidth to be accelerated. Next is the new GPU architecture, and I want to give you some more details on it and the new capabilities that is bringing and will bring into the market. So PVC or Ponte Vecchio, as known externally, let's say, as already said before, is going to be introduced, will be introduced later this year. It will leverage on the latest technologies for the packaging and the manufacturing, also bringing third-party manufacturing components inside of it. So it's going to use not just Intel capabilities, but also TSMC, as you can see here. We can scale, obviously. We can scale up to all GPU, up to 8 GPUs, sorry, fully connected all together through what we call Axi-Link, as you can see here also from the design. But the bus for the communication between CPUs and GPU is going to be the PCI Gen 5. Interesting features on it, or main characteristic, let's say, to start, this will be the significant amount of level 1 cache, which will be up to 64 megabytes, or the overall level 2 cache, which is up to 408 megabytes, all connected with the HBM2E, which will be even obviously larger and significant. The other things that I want to highlight about PVC is that on top of the computing capabilities, we will also have ray tracing units incorporated into the device. And there will be obviously different kind of SKUs up to 128 Xe core for the highest, let's say. How it will appear, how it will be in some way delivered into the market. So Ponte Vecchio is going to be available again on a integrated in an open standard, let's say, package, which we call OEM, that will be installed in a different subsystem. You can see here the 4 subsystem, the by 4 subsystem that also allow the communication through the Axi-Link between all 4 GPUs, and that could be integrated in a typical, let's say, let me call it kind of standard unit of HPC compute device, right? As you can see here on the right side of the pictures, that could be combined with the 2 Sapphire Rapid CPUs, for example, in a single one U node, right? All cooled by liquid cooling solutions to have a very advanced design capabilities. Who is going to be our main, let's say, partners to deliver that the product into the market, to bring the product into the market? Obviously, we are working with most of our usual partner. You can see a few of them mentioned here. So from Atos to Dell, HPE, Supermicro, and Lenovo, and the others. And that is these are the ones that will bring, as I said, PVC installed in their system in 2022 and beyond. Another important thing that I would like to highlight today is that, as I said, Intel is working on an open initiative. We are collaborating, and you have seen many announcements recently about investment in Europe. And one of them is also related to the agreement, the collaboration with Sapphire, because we want to allow and bring to the market another opportunity to let's say to deliver Ponte Vecchio with another partner and a different kind of architecture, to combine that with a different kind of architecture. And again, the glue, let's say, between this different kind of architecture and PVC will be the oneAPI initiative, right? So that's allow us also to bring the PVC and the compatibility and so on to the market. And beyond that is also part of the more large strategy, as you know. So Europe is very important for Intel, and we want to enable the next exascale building, let's say, also in Europe, and that is basically what we aim to do, to collaborating with Cyprus and other centers in Europe in general. And that, I would say, is all from my side on the hardware. If you don't have, if you have any questions, happy to try to answer. Otherwise, I'll leave the stage to Giacomo, and we'll have that will go in details about the oneAPI.
There are a few questions on the chat that I will answer, I think, on the chat. So.
Okay. Otherwise, I can answer even.
So I think the question was, are the nodes that you show the same as the ones that will be in the Aurora system?
No, this is a standard HPC, I would say HPC node, classical 1U node. The Aurora node is different, as you have seen publicly on the picture. The Aurora allow to install up to 6 GPUs. It's a very high dense specific design, while this one that I was showing in the picture is just up to 4 GPUs, not more.
Okay. And the other question is, can you comment on the coherency of communication between CPU and GPU? So I don't know if we discuss that here or on the next part. It's not there. So actually the introduction of CXL has been only announced for the CPU parts. I cannot comment, I cannot say anything about the GPU currently. So okay. Thanks a lot. And okay. So I think it's all I can see. So thanks for this hardware introduction, Andrea. And I think we can now move to Giacomo's part, so more dedicated on our software strategy and oneAPI.
Thanks to you, and let me stop sharing. So I will give the stage to Giacomo.
Okay.
Thanks, Andrea. So let me share. This. And then can you see my slides?
Yeah.
Okay, perfect. So welcome again. I'm Giacomo. I'm an application engineer and so my main task is to enable customer first on Intel CPUs, now on Intel GPUs, and in particular, I'm focused on OpenMP for offloading for Intel GPUs. So let's start to talk about our strategy for the heterogeneous computing from the software perspective. And in this talk, I'll give you a brief introduction on oneAPI, and then I'll focus a little bit more on OpenMP offloading, especially for Fortran, because I know that most of EUROfusion code are Fortran based. So I'll talk a bit more in detail about that. So as you know, each kind of data-centric hardware typically needs to be programmed using different languages and libraries, right? So you need to maintain separate code bases. And this leads to an inconsistency between the supports and the tools between the different platforms. And so the developers have to waste time learning different sets of tools. And so in order to develop software for each hardware platform, you need to invest any time that you want to develop for a new architecture for a new, for instance, accelerator. And this leads also to a little ability to reuse that work to target a different architecture. oneAPI industry initiative delivers a unified software development environment across CPU and the accelerator architectures as GPU or FPGAs. The good point, the very good point, the strongest point, I think, of oneAPI industry initiative is that it is based on standard and open specification. Let's say, choose the best accelerated technology and don't let the software to decide for yourself. The fact that it's based on industry standard, let's say, gives you also a safe and clear path to the future. And considering heterogeneous computing, oneAPI supports two methods for offloading the data to GPUs or FPGAs. Data parallel C++ for C++ code, and OpenMP offload for Fortran and C code, and even for C++ code if you want. This is a picture of in which there are about 100 of organizations that support oneAPI ecosystem, and here are listed the national labs, supercomputing centers, universities, and also vendors. So there is really a broad support of oneAPI. So let's focus now on data parallel C++ first. Just a couple of things about that. Data parallel C++ is the oneAPI implementation of SQL. This is an high-level language that is designed for data parallel programming productivity, and it is based on the C++ language. And DPC++ provides full native high-level language performance on par with standard C++. And it simplifies the code migration from proprietary languages with providing a programming model that is familiar to GPU software developers. The starting point of data parallel C++ is SQL, that is developed under the industry consortium Kronos Group. Intel is addressing the gaps in SQL languages using extensions that then we will drive into the standard. We also included in oneAPI a source-to-source compatibility tool that assists you with the migration from CUDA code to DPC++. And I'll talk about that later. OpenMP is an industry standard since 1997. It's compatible, as I said before, with Fortran, C, and also C++ languages. And so as you all know, OpenMP started with shared memory parallelization. But in 2013, they introduced the possibility to offload the computation to any kind of accelerator with OpenMP specification 4.0. OpenMP standard is not linked to a particular vendor nor accelerator type, and is based on directives as the standard, the OpenMP for CPUs. And just a little story. So, as I said, OpenMP 4 introduced the target terminology, and so the possibility to offload. The version 4.5 of the OpenMP specification added the device memory routines and constructs for device data mapping. And the version 5 introduced the Fortran interfaces for device memory routines And sorry, the 5.1 introduced the Fortran interfaces to device memory routines. And the last release, OpenMP 5.2, consolidates the accelerator support. Here you can see all the members of the ARB, that is the entity, the architecture review board that takes care of OpenMP standard. As you can see here, there are labs, universities, but there are also, let's say, all the GPU vendors that are now out in the market. So not only Intel, but also NVIDIA and AMD. I don't know if you can mute yourself if you don't want to ask some questions, please. And so in this slide, you can see the compilers that supporting OpenMP support OpenMP offloading. I took this data from the OpenMP website, and so you can see that the list is not so big, but there is a pretty decent support for OpenMP offloading. So we have Intel oneAPI compilers for Intel GPUs, the AMD AYOMP compiler that provides support for multiple GPUs, not only AMD, the FLANG and CLANG compilers that support NVIDIA GPUs, NVIDIA, the GNU compiler that supports both NVIDIA and AMD, then the HP compiler, the IBM compiler, and the NVIDIA HPC compilers that support NVIDIA GPUs. So let's introduce briefly the OpenMP device model. So OpenMP is host-centric. So there is, and there will be always an host for traditional multi-threading. And there are multiple accelerators. There can be multiple or just one accelerator coprocessor of the same kind for offloading. The device model includes support for moving and establishing, allocating data on the target device, defining hot region that will run on the target device, and also provides tools for defining parallelism and work sharing on the target. It's important to highlight that this device model treats the transfer on control from host to device, the movement of data, and parallelism as separate entities. So how the program execution model for OpenMP offload works? As I said before, everything starts from the host. The heterogeneous execution model is host-centric. There is an initial thread that runs on the host. Before OpenMP 4.0, there was permitted just one initial thread for the program. When they introduced the possibility to offload to accelerators, coprocessor, or GPUs, they introduced also the possibility to have multiple initial threads inside the same program. This because the thread that encounters the target construct, the target construct is the construct that define a region that should be run on the device. This thread that encounters the target construct does not execute the target region. It creates a new initial thread on the target region. And the initial thread on the host waits for the execution of the target region to complete. And after the execution of the target region finished, the initial thread on the host continues executing the code after the target construct. And the initial thread that has been created on the accelerator can potentially run the task on the accelerator. Why potentially? Because it is possible that the application runs on a machine without accelerators, or that, for instance, the target construct as an if clause that for any reason is evaluated to false. Under these circumstances, the new initial thread will run on the host, not on the accelerator. And this is the thing that allows OpenMP applications to be portable among systems with and without accelerators. And there is also another reason. These two different initial threads, so the host initial thread and the accelerator initial thread, make possible that host and target region can run in parallel under several circumstances that the developer can define. And so the CPU can be kept busy also when there is another task that is running on the accelerator. It's important to point out that any initial thread creates its own contention group. The contention group is the set of all the threads that are descendant of the initial thread. And so any target region is a different contention group because any target region creates a new initial thread on the accelerator. And it's important to say this because the threads that are in different contention group cannot synchronize with each other. And when threads from different contention groups execute in parallel, only the variables that are written through atomic construct by a thread in one contention group can be read by a thread in another contention group, and only if they are executing on the same device. So now let's start to offload. I put here some practical example from, let's say, Intel point of view of OpenMP offloading. So the easiest way to offload your existing code with OpenMP is by trying to accelerate the mathematical library codes. So here, for instance, this is an example for Quantum Espresso code. As you can see, there is this routine. I don't know if you can see the pointer.
We cannot see the pointer.
Okay.
I think it no, it's okay. Sorry, no, it's okay.
Okay, right. So there is this routine that inside calls this function, this mathematical function. The easiest way to accelerate, you can easily accelerate this function, modifying your code in this way. So you just need to introduce these little and short statements, and you transfer the execution of this function from the CPU to the GPU. Now let's discuss a bit in detail what you need to add here. The first thing that you need to add is you need to include the MKL file that contains the Fortran interfaces of the functions, of the mathematical functions. Then you need to use sorry, the modules for LAPACK, because this function is one of the LAPACK set, and you can use or the 64-bit flavor integer flavor or the 32-bit integer flavor, depending on what you need. Then one thing to remark is that for MKL, the data is not automatically transferred to the GPU. So the developer needs to take care about data movement between host and device. If you want a mathematical function run on the device, you need to prepare the data environment on the device accordingly. And this is how you can do it. So for instance, here we use the target data map construct from OpenMP. So we are transferring H and S to the device memory, and we are saying that we want this other data back into the host when this region is finished here. And then the last thing you need to do is to add this pragma this is an Intel extension, is not an OpenMP standard. I'll talk about it later. And this construct dispatches the call to the MKL GPU function instead of the standard CPU one. So with this, we are saying to the to the compiler, please create a code path that call the GPU function and not the CPU one, and transfer the execution to the GPU. So as I said, this target variant dispatch is an Intel specific extension, is not in OpenMP standard. This is because when MKL started to develop the offload for OpenMP, so OpenMP has nothing like that inside the standard. So Intel decided to create this extension, and then something like that is added in the standard, and I'll talk about that in the next slide. But by the way, so as you can see, this construct move the execution from the CPU to the GPU and call the GPU version of the routine. This is the MKL interface for DGEM. I took DGEM. As you can see, there is the GPU function and the CPU function that shares the same interface. The interface is the same. So the only way for the compiler to distinguish between this function and this function is to put this statement inside the base function, the CPU function. This is telling to the compiler, and this is OpenMP standard. This is telling, hey, this function, the base function, the CPU function, has a variant that is calling in this way, MKL plus DGEM OMP offload ILP64. And so you know that there is another function that shares the same interface with the base function. And you need to call the variant function, so this one, instead of this one, when there is the target variant dispatch construct before the function call, as we saw in the previous slide. And this just specified that this variant function is activated only if the ARC, so the GPU architecture is GEM, that is the code name for Intel GPUs. In the future MKL releases, will be introduced the dispatch construct. So dispatch is the, let's say, the OpenMP standardization of the target variant dispatch. So instead of putting OMP target variant dispatch and then the function call to MKL, to the MKL function, you need just to use OMP dispatch. This is, as I said, standard that's been introduced in OpenMP 5.1. And anyway, inside the MKL interfaces, you will see always the declare variant thing, because this is the only way to make the compiler able to distinguish between this function and its GPU variant. So Intel rmkl is available in the Intel oneAPI based toolkit, but if you want to use it with Fortran and MPI, you need the Intel oneAPI HPC toolkit. I'll talk about that later. oneMKL includes all the function that you already know, the mathematical function that were in the old Parallel Studio, let's put it this way, plus OpenMP offload and DPC++ interfaces to run MKL computations on Intel GPUs. And this is a list of the functions that already support GPU offloading with both OpenMP and DPC++. So BLAS123, LAPACK, FFTs, and vector statistics with basic random number generators. So one thing more, the second thing that we, as you have seen in the slide on how to accelerate MKL calls to the GPUs, you need to transfer data between host and device. And this is called in OpenMP data mapping. OpenMP is OS-centric, so it has this concept of data mapping, and it is used to map to host data on the device. Mapping means that you allocate something on the device based on the data that is already on the host, and eventually you associate the host and device data, and you also have the tools to sync device and host data. So for instance, here, as you can see, there is a routine. This is for Quantum Espresso 2, a routine that allocates some data on the host. In order to, if you need any of this data on the device, what you need to do is to add this, for instance, this directive that in this case are allocating the same data that you have allocating on the host, so with the same size, with the same indexes and so on the GPU memory space. And so you can use this data, for instance, on the GPU memory space. This clause say that you are just allocating, you are just reserving space. You are not transferring the content of the CPU data to the GPU data while allocating. There is another clause that is 2 that permits you to at the same time reserve a space on the device and transfer the content of the CPU data into the device memory space that you just reserved. Yeah. And OpenMP provides several constructs for data mapping. The most simple is the target data map. With this construct, data is mapped only for the extent of this region. Then, and so when the program hit the end of this region, the data that you mapped here at this point of the program, so after the end target data, is not accessible anymore on the device. Then there is the target ender data map. That this is a standalone directive, as you have seen I used in the previous slide. So if you wanna map something on a dedicated routine, for instance, you need to use this construct. This is a standalone directive, and the data is mapped on the GPU, let's say forever, up when the program encounters this construct. This is the standalone directive that unmap the data that has been mapped using this one. And then you can also map data directly when you are opening a target region, because I forgot to say something about that. So this construct here is not transferring the execution on the GPU. So this construct here means only that you wanna allocate something on the device, so the data that you put here, and eventually you want to transfer the content from host to device. And at the end of this region, you want, for instance, copy back something from device to host, but you are not moving the execution from the CPU to the GPU. You need target. This is something a bit confusing. At least this is a bit confusing the first time for me. So this target OMP target data is just for data mapping. If you want to transfer the function, the execution, sorry, from CPU to GPU, you need to use OMP target, and you can map data when you are transferring the execution from the host to the device. And so this construct here means that you are transferring the execution from host to the device, and you are mapping some data for the extent of this region from host to the device. Yeah, so everyone that is familiar with OpenMP offloading, please stay here. For the other, just some very good best practices not only for OpenMP but for GPU programming. So everybody knows try to keep data on the GPU as much as you can. And one important thing for OpenMP is that OpenMP has some predefined mapped for the data types. So, for instance, it could happen that your program work if you open a target region, you transfer the execution from host to the device, and you don't map anything because OpenMP has some predefined mapping. But the point is that you shouldn't rely on implicit mapping, so on the OpenMP predefined thing, because you can specify in this way when a variable needs to be copied to or from the device. And the good thing of the target enter and target exit data is that you can manage data transfer more explicitly, and you can, for instance, isolate the data transfer in the same context when you allocate something on the host. And one very important thing is the last one. And I discovered it, let's say, because I enabled a CPU program for Intel GPUs using OpenMP, but that program wasn't working as I expected. And at the end of the day, what I found is that I haven't mapped explicitly scalars. And so the point is that when I tried to run the modified code on the CPU, disabling offloading, the scalars were not made in first private, so the code was running wrongly. The point is that in OpenMP, for instance, in a parallel region, the standard OpenMP parallel region, a standard is not made first private by default. This is something that happened. I then talked with OpenMP ARB members. So they told me the point is that at the beginning, when they introduced the offload, they decided to use the same behavior for the scalars that they were using in the parallel region. So no default behavior. The point is that they observed very bad performance with that thing. So they decided to make first private the scalars in target regions, and then they can reach decent performance. The point is that they introduced a different behavior from target to parallel regions. And so please take this in mind when you enable your code using OpenMP offload. So now how you can transfer the execution to the GPU, we already talked about this briefly before. So with the target construct. So for instance, if you are considering a simple loop, you can offload this loop and transfer this assignment to the device. This is pretty easy. You just need to decorate your loop with this constructor. So this is the construct that moves the execution from CPU to GPU. And here you are creating a teams of threads, and you are distributing the different iteration, and so you collapse the loop. So you are distributing all these iterations through the different threads that belong to this team. Now, what if you wanna, for instance, offload this loop here, but this loop called a function, right? That is defined in another module, okay? This is what you need to do. So you can use the same construct that we used here. So the target teams. Now here I use a different flavor, so loop. But it basically do the same of distribute, parallel, do, SIMD. So if you put, at least this is true for Intel compiler. So if you put loop, the loop construct does the same of distribute, parallel, do, SIMD construct. The point is that here we are calling a function, And so you can do it, of course, but you need to modify your function. So you need to put this construct inside the function OMP declare target. Because with this construct, the compiler generates a CPU version of this Saturn 0D routine and a GPU version of the same routine. The CPU version will be called inside the host region, while the GPU version will be called when the function is invoked inside the target region. So in order to make this function callable from a target region, you need to declare the function as target. And this is pretty simple to check if you forgot to do it, because Intel compiler will complain about that it cannot find the symbols for this function. Okay, because the compiler has not generated symbols for the GPU. And this is something that we already seen in the MKL interfaces. So it can be that so you can have two separate routines that that do the same thing, but one is for CPU and one is for the GPU. So in order to and they have the same interface. So in order to make possible to the compiler to distinguish between the two routines, you need to put inside the base function the declare variant thing. You can specify, you specify the name of the variant function, and you are saying call this function when the construct that is before this function match the dispatch thing. This is OpenMP standard, nothing related to the target variant dispatch for MKL. And so this means that in your code, when you simply invoke the function in this way, you are calling the CPU flavor of the routine. While when you invoking the function in this way, so with OMP dispatch and then the call to the routine, you are calling the GPU flavor, and so you are offloading this routine to the GPU. The last thing is so we already talked about data mapping, but what if you want to allocate something only on the device? Because if you remember, data mapping is only for data that is already on the host. So if you want to allocate something on the device, OpenMP introduced from version 4.5 of the specification the device memory routines. These routines that are listed here, these are from the last version of the specification, because OpenMP added a couple of them during the years. So these routines permit to allocate, deallocate, and also manage the pointers, copy data between a device pointer and the host data, and so on. The point is that from OpenMP 5.1, this routine also have a Fortran interface, but as you can see from here, this is the Fortran interface of the device. For instance, I take the OpenMP target alloc. So with this routine, you can allocate a pointer on the device memory space, something that is not allocated on the host. But this is the Fortran interface of this routine. So as you can see, it's just C binding of the C function. So in order to use it from a Fortran program, you need to do all these kinds of tricks. So you need to use, of course, ISO-C binding. You need to declare some C pointers, and also you need to use the C int type, and then you need also to, for instance, to allocate something on the device memory space, you need to use the C pointer as a dummy pointer, and then you need to evaluate the byte size of the data that you want to allocate basing on the indexes, for instance, because the OpenMP device memory routine needs the byte size. And then you need to associate the C pointer that you have allocated on the device to the Fortran pointer, and eventually specifying the dimension. So if you want that the Fortran pointer will not start from 1, for instance. Intel introduced some extensions to the device memory routines. Let's say to the device memory routines. This is the first group. So these are extensions to the device memory routines that permit to allocate data directly on the device, on the host, or on the shared memory. And then Intel introduced also this other extension that permits you to use the standard Fortran allocate construct to allocate data on the device memory. So you need to create, let's say, allocate this allocator that takes care about the target memory, the device memory. And then you can just use the standard Fortran allocate. And at the end, you can deallocate data with the standard Fortran deallocate. And so you have allocated something on the GPU without using the device memory routines and their weird interfaces. Or you can try to use DMR. DMR is, I developed this library. This is an open source Fortran library that exposes pure Fortran interfaces for OpenMP device memory routines. So you don't need to mess up your code with include SOC binding, declare C pointers, nothing like that. You just need to declare a variable as pointer and then call, for instance, the routine of DMR that takes care of data allocation, and that's fine. And there is also in this slide, I would like to put another project because we are trying, how to say, to improve the developer experience with OpenMP offloading. So DMR is one. The other important project that is developed by Harald, a colleague of my group, is the OpenSCC to OpenMP tool. This is a Python-based tool for code migration from OpenSCC to OpenMP. And the code will be released soon as open source project. So I can give you details in the next week if you want to try it. I don't know if you want to start with questions and then move, if there is time, to the tools. What do you think?
Yeah, so Giacomo, I think you're doing good on time. So there is half an hour remaining. There have been 1 or 2 questions on the chat, and I think Chris answered it. So I think we're good. But you're right. I mean, knowing your presentation, I know now that you will be moving to another part, which is more focusing, you know, on our specific tools, which are inside the oneAPI, just not only programming models. So yeah, this is indeed a good time to take questions live, if there are any, on this more programming model side of the presentation. Is there any? If not, we will go on. So I think, Giacomo, you can go on and focus more on you know, all the great tools we have inside oneAPI.
Okay, let me come back. Okay. Yeah. So let me just share with you some details about the oneAPI toolkits. So the oneAPI products are in production from December 2020. The Fortran compiler, the new Fortran compiler, I'll talk about it later, is in production from this year, right? So from the first release of this year, also the new Fortran compiler is declared ready for production. The oneAPI toolkits are available from Intel website. freely available, and the premium support is offered as a separate purchase. The cadence of the product release is quarterly. So any quarter we will release a new version of all oneAPI toolkits. So as you can see here, there is the base toolkit that basically just provides you everything you need for C++. If you want to develop something for Fortran, C, and also using MPI and OpenMP offload, you need the HPC toolkit. I think that this is, let's say, the base toolkit, as the name says, for you that you are doing HPC. So I think that you will find it installed on any HPC system that you are using. And then there are also tools for AI, for Internet of Things, and also for rendering. The good thing of AI is that this toolkit accelerates machine learning and also includes high-performing Python libraries for both CPU and GPU. So if you have a code that uses Python, for instance, I strongly encourage to download this tool and use the Python version and the Python library that are shipped with this tool if you are targeting also Intel CPUs, because the performance increased really a lot. So this is a slide in which there are both the base and the HPC toolkit. So with the clear blue are the components of the base toolkit, as you can see. With the darker blue are the components of the HPC toolkit. So you can see that with HPC, you have all the compilers. So you have, sorry, this is wrong, because now the Fortran compiler is in production, is not in beta anymore. So you got the C++ and the C and the Fortran classic compiler, the compiler that you well know, so ICC, iFort, ICX. Then you have also the new compilers based on LLVM that are IFX, ICX, and ICPX. And they are, at least for C++, for C and Fortran, are the only compilers that can, let's say, enable your code for OpenMP offloading, but we will see it later. Then you have the Intel MPI library and a lot of other libraries. So the DPC++ library, if you are using DPC++, the oneMKL library that, as I said before, contains all MKL functions that you well know from Parallel Studio. So all the let's call all the MKL functions for CPU, and then the GPU flavor or that functions for GPU offloading. And then there are also libraries for threading building block, for data analytics, and so on. And the tool also contains the tools that I think you already know. So for instance, Intel Advisor, Intel vTune, and also Intel GDB for doing debugging on both CPU and GPU. And then the HPC toolkit adds to the base toolkit also the Intel Cluster Checker. That is a good thing, but this is more for HPC administrators, because it permits you to easily check, for instance, the health of your cluster, and then also Intel Inspector and the Intel Trace Analyzer and Collector. So briefly, so the DPC++ compiler, as you can see, is based on Clang LLVM, and then upon the DPC++ runtime, and it can target CPU, GPU, and FPGAs. The same for the next-gen compilers. So with the classic compiler, you can only use CPUs. If you are using the new compilers shipped with oneAPI HPC toolkit, you are using the LLVM backend and the new OpenMP runtime that can also offload your code to GPUs and FPGAs. So this is just a simple slide to show you how our compiler works. So there is the different languages front end, so the Fortran, C++, or C front end. Then there is this the front end creates this intermediate representation. Then there is the LLVM optimizer that creates another, let's say, the optimized presentation. And then the LLVM code generator that produces the .s file. And this is, let's say, here you can see how the compiler is split between front end and back end. So you can see that the front end moves the source code to an intermediate representation, and then the back end takes care of optimizing, generate the code, and also generate target code. So code for accelerators. This is a table that makes summary of what I already said. So the classic compilers, so C++ compiler and the Fortran compiler classic, just have CPU target. If we are using the new oneAPI compilers, I want to clarify that you can find the classic compiler also in the latest release of oneAPI. So oneAPI, these are all the compilers that are shipped with oneAPI HPC toolkit. The classic are just for CPU, and the new compilers, IFX, ICX, ICPX, and DPCPP compilers are for both CPU and GPU, and for also OpenMP offloading. One thing that I mentioned before is the compatibility tool. This is shipped with the base toolkit, so you can find it also in the HPC toolkit. This tool minimizes the code migration. It's trying to make a bridge between the CUDA and DPC++ language. This tool assists you to migrating CUDA apps to DPC++. And this code runs pretty well, honestly. So we estimated that 95% of CUDA code can be transferred automatically from CUDA to DPC++. And when the code, the tool is not able to translate your CUDA code, it provides you comments and uncharged CUDA code and hints in order to help you to migrate that part manually. Then there is the VTune profiler. So these are all tools that you already know, and there are I think that you already used on Intel CPUs. Now we enabled that tools for offloading. So you can analyze not only the CPU code, but also the GPU code. And so you can tune the DPC++ performance or OpenMP offload performance. You can analyze the GPU execution, the data transfer, and so on. So we, let's say, added all the capabilities to help you to optimize not only the CPU code, but also the CPU and GPU code. The same for Advisor. So now it has roofline analysis, not only for the CPU, but also for the GPU. And so also in this case, you can optimize the threading and the vectorization of your code, not only for the CPU, as you did in the past, but also for Intel GPUs. And the good thing of Advisor it's that it also provides an estimation of the performance gain for your base CPU code if you want to accelerate it. So Advisor analyzes your CPU code and highlights the regions that from which you will take more profit to offload, and estimate the speed up that you get if you offload that regions. Then there is GDB. So as I said before, you can use GDB not only for Intel CPUs, but now also for Intel GPUs and FPGAs. And during the runtime, GDB auto-detects the accelerator architecture, and so it turns on the correct behavior depending on the hardware. As I said before, the oneAPI toolkits are freely available from Intel website, and you can download it using, let's say, distributions like oneAPI or as archives that you need to unpack and install on your system. One mention here to Intel Dev Cloud. So Intel Dev Cloud is a development sandbox in which you can develop, test, and run workloads using Intel CPU, GPUs, and FPGAs with oneAPI software. In Dev Cloud, you can find the state-of-the-art of so the latest release of oneAPI, and you can find Xeon CPUs, Atom CPUs, and also Intel GPUs. So you can find both integrated and discrete GPUs. And the registration is free. So you can go and search for Intel Dev Cloud, register, and get access and start to code on Intel GPUs without downloading anything, without the need to have the hardware physically, because everything is on the cloud. And this is just for the priority support. As I mentioned before, the tools are free available, but if you want and if you need priority support, you need to purchase it. And for instance, this is if you already have priority support for Intel Parallel Studio, you can move that priority support to HPC plus based toolkit. So you don't need, if you already have, let's say, a license for Parallel Studio that is giving you priority support, you can download HPC toolkit and you can transfer. There is a link in Intel website that guides you to the transferring process, and so you can transfer the license from let's say the Parallel Studio to the priority support of HPC and base toolkit. And this is the last slide. So here you can find the resources of that we make available for oneAPI. So here you can download the code, the tools, and you can find documentations and code samples, and also you can register on Dev Cloud and start to code there. And we also provide training and webinars. And there is also the website of the oneAPI industry initiative with all the industry specifications. And we also provide community forums, and there are also academic programs. There are we created Center of Excellence of oneAPI for enabling code research and teaching the oneAPI industry initiative. That's it. And thank you.
Okay, thanks a lot, Giacomo. So yeah, I think I was saying you're doing good on time. So I think we are 10 minutes early, and we wanted to be 10 minutes early just to be sure we could answer any questions during this webinar. So I think now is the time if you have any. I have not seen any more on the chat, Giacomo, for your information. So
Okay.
I think we're okay. But yeah, please feel free.
I don't see question either.
Okay.
Please
And I don't know if
let's go.
someone of the Intel colleague want to add something, please do it.
No, I think we are good. I mean, the goal was really to give you so this quite long introduction about our tools and everything.
So may I make a question?
Sure.
Sure.
Hello, this is Simpa from Finland. So I have a relatively recent Intel laptop with some internal GPU there. How relevant it is for me to try with this existing laptop GPUs to start GPU programming and using the tools? How do they compare to the actual HPC GPUs we are expecting from Intel?
If understood correctly, you are saying it's let's say good to start to try to program on your laptop, something like that.
Yeah, I think that's the question.
Yeah.
I mean, people have some laptops or workstations, and
well, yeah. The thing is that probably, or not probably, so for sure, your laptop has an integrated graphics. So the integrated graphic shares the memory with the CPU. So I think that it's good to start to program in there, because you can start to look how to translate your code, check if your code is working. It's fine, I think, and it's good practice also, because it's something that you can control easily, right? But the point is that you cannot measure performance there, and you can be also that you in this way you hide some bug, for instance, due to the data transfer, because CPU and GPU share the same memory on your laptop, right? So it's not what happens in the HPC nodes, where CPU and GPU does not share the same memory. And so you need to explicitly map things, you need to explicitly transfer data, and you need to take a lot of care of properly data synchronization between nodes and device in order to avoid the incorrectness of inside your code. But I think that it's a good starting point. And if you are using, for instance, an Ubuntu-based distribution, or if you are using OpenSUSE or even Fedora distribution, so a CentOS-based, there are already, as I said before, Intel packages, APT packages, YUM packages. So it's pretty easy to install the base toolkit, the HPC toolkit, and it should also automatically install all the drivers that you need. And so it's pretty simple to do.
And to give examples, I mean, in France, I have at least, 2 or 3 labs who started their work on oneAPI using, so what Giacomo was mentioning, some internal graphics, so Iris graphic, like, quite old ones, to be honest. But they have, they have double precision support and this kind of thing. So, I mean, if you're interested, you can also, send us some, details about, what CPU you have, and we can tell you, if there is any limitation or anything like that. But no, that's a good idea, and that's something actually I'm using a lot in France with some labs.
Alex, not only in France, I think particularly when we started the work porting applications from CUDA, for instance, to oneAPI and to the Intel hardware available 2 or 3 years, the Intel integrated graphics was a good choice to start the work, and also trying it out on early hardware, because the execution units have a lot of similarities what the discrete graphics gonna have.
And the second, then the second option is also to use DevCloud, but it's you know, it's a remote access, but that's another option that it's quite easy to try.
Yeah, one thing to remark is it's better to use some supported distributions. For instance, on my personal PC at home, I'm using Arch Linux, and honestly, I'm still not able to make everything work. So I installed the packages using the archives, of course, not the apt or the yum packages. So I downloaded the tar.gz archives. Everything is installed, but there is some problem with drivers. Instead, if you are using a supported version, so as I said, the Ubuntu, but they are almost all. Arch is a bit, let's say, bleeding edge. So if you're using Ubuntu or CentOS based or OpenSUSE, you are really rock solid.
What about ready containers? And if there are any?
Yeah, there are also containers. So you can also try, if you go into this website, that you can find everything we make available. So not only the packages, but also containers. I don't remember if there is also a container for the HPC toolkit or not. I don't know if Edmund remember that, but we can check.
Yeah, there is indeed a website with containers.
Okay.
There's another question on the chat.
Yeah, I need to open it. Okay. oneAPI, support ICX, ICPX. Well, I mean, I don't quite understand the question. So ICX is the next generation compiler for C language. Is the compiler that enables OpenMP offloading. If you are using the old ICC with a C program, you cannot offload using OpenMP. ICPX is the C++ new compiler that also permits you to offload using OpenMP. If you are using ICPC, the old one, you cannot offload to the GPUs. This is because we modified the backend. So we moved from our proprietary backend to the LLVM-based backend. And this enables the offload. The DPC++ compiler is a compiler that supports C++ and also DPC++. So the Intel extension of SQL that permits you to offload C++ codes using DPC++.
But it's still standard C++.
Yeah.
With additional header files and stuff, but it's not a completely new language like this.
Yeah. So you, in theory, I think not in theory, you can use the DPC++ compiler for your C++ code. You can use it. Because as Chris said, DPC++ embeds all the standard C++. So the compiler will manage your C++ code flawlessly. I don't know if I answered to your question. Perfect. And Yeah, I don't know, maybe this is just a question for you. So the main focus of this presentation was Fortran, let's say OpenMP offloading, and I took Fortran examples, but for she are straightforward. Let's say there is not the part for device memory routines, so they are straightforward in C. In Fortran, you need to mess up the interfaces. But anyway, I focused on OpenMP offloading because I know that, as I said before, the majority of the code that you are using are based on Fortran. So this is Intel for Fortran decided to go with OpenMP offloading in order to enable GPU acceleration. If you want to know more about DPC++, because you are interested in C++ acceleration using SQL, we can organize another meeting with some other colleagues and maybe present something about DPC++ there. So let us know.
I take the point on that, but that's a good proposition. Thank you very much.
And
Thanks
also,
a lot. Yeah, I think
yeah,
we're right on time.
Just one last thing. If I'll provide you the slides, and I think that I don't know if Andrea can provide them, but I'll provide you, and I'll write you my mail. So if you have further questions, don't hesitate to contact me about that.
Yeah, we can share both slides. The content that we presented today is all public, so that's fine.
Perfect.
So Giacomo, I think the best would be to send the presentation to France, and I think
Yeah,
would distribute.
I'll do that. Mm-hmm.
Okay.
Absolutely. Perfect. Then I will take care of releasing the slides on the EUROfusion website. Okay, so I don't see any other question.
I put in a link for people who are interested to read more about the background on DPC++. There's a book. One of the co-authors is one of our evangelists, James Reinders. So I put a link in there to Amazon. It exists also as a free, so you can Google for it and even can download a PDF version if you want to.
Thank you very much, Edmond. Is there any other question? Okay, I don't see any, so I will stop recording.